Ready to start? Okay, ready to start? Right, so we have 2 more to go after this, right? So then we'll have a final exam, right? Then the semester will be end. Okay, so let's start with one definition. Okay, I want to introduce the definition of a characteristic of a ring. Okay, characteristic of a ring. So before that, do you remember that there's a unique ring homomorphism? Okay, let's call it phi z to any ring R. Okay, any ring. R is a ring. Okay, so what's this unit map here? Okay, you send all the positive integer, okay, to the addition of multiplicative identity n times. Okay, and then you send all the negative integer to where? To the negative of p of negative. Okay, or the inverse of the additive of multiplicative identity n times. Okay, so this is a unique map we have shown last time. So we'll define that the characteristic of a ring is the non-negative integer n. Okay, what does this non-negative integer do? This is the generator of the kernel of the homomorphism that we have above. So this means what? Okay, this means that if for example, if if let's say n equals to 2, okay, then this 2 will generate the kernel of phi. Okay, so meaning what? To have this homomorphism to work, this means that 2 plus 1 plus 1, 2 times, okay, equals 0 in your ring. Okay, so for example, what is the characteristic of the ring? Characteristic of, let's say, Z mod 3Z. What is the characteristic of Z mod 3Z? So you consider a map, a ring homomorphism from Z to Z mod 3Z. What's the kernel of this map? What's the kernel of the map from Z to Z mod 3Z? Yeah, what's the thing get sent to 0? everything there, mod 3. So meaning everything generated, the kernel of this unique homomorphism from integer is generated by 3. So the characteristic is 3. You can see that 3 gets sent to 0 in Z mod 3. Z mod 3Z. For example, again, so let's try again. So what's the characteristic of, let's say, Z mod NZ is what? Is N. Okay, it's N. Okay, no? So why is it 3 for Z mod 3Z? Because kernel of the ring homomorphism from Z to Z mod 3Z is generated by 3. Okay. Similarly, for Z mod NZ, the kernel of the map from Z to the ring, okay, is generated by N. Okay, so this is a terminology we might use later. Okay. Any question for this characteristic of the ring? All right. Next, let's recall something we have done. Okay, recall the quotient rings. Recall the quotient rings. Zi I minus 2. Okay, last time we showed that this is equivalence. This is isomorphic to F5. Okay. Last time I showed that this is isomorphic to F5. How do we show this? Okay. So one way we show this is we rewrite the ring Zi over I minus 2. Okay, this ring is actually isomorphic to Zx quotient by x squared plus 1 and then quotient by x minus 2. Okay or not? Because I is the root of x squared plus 1. Okay. So there's a theorem says that if we are quotienting out by ideal generated by multiple generators, we can quotient any multiple first, any generators first. Okay. It's like you want to divide 6 by 2 times 3. So you can do 6 divide 2 and then divide 3. Or you can do 6 divide 3 and then divide 2. Okay, so this is the same logic here. So we can quotient the polynomial ring by the ideal generated by x minus 2 and then quotient by this x squared plus 1. Okay. So if I quotient zx by x minus 2, what do I get? What I get is just z. Okay, so I think I should better write down the isomorphism for you. So what is zx over x minus 2? Okay, so I claim that this is isomorphic to z. Okay, I claim that this is isomorphic to z. How do you show this? What's the isomorphism you should write down? So this is a isomorphism involving the quotient ring, right? So you should use first isomorphism theorem. Okay, how to use first isomorphism theorem? You need a surjective map. Okay, you need a surjective map. So you need to construct a surjective map from Zx to Z. Okay. Such that the kernel of this phi is the ideal you quotient by. Right, so that by first isomorphism theorem. You will get the map, the canonical map from Zx to Zx quotient by the kernel. And then you have a isomorphism here. Okay, so this is the what given by the first isomorphism theorem. So the problem is, what's this surjective phi you should take? What's the surjective phi you should take here? So to create a map between rings, right? Okay, you need to tell me where the polynomial should go. Okay, where the polynomial should go. But to tell me where the polynomial should go, you just need to tell me where the variable go. Okay, and then the other will be extended by homomorphism property. Okay, so where should this S go? S should go to where? Sorry, 0. S should go to 0. You sure? What's the kernel of X going to 0? Nothing goes to 0, right? Other than X. Okay, but we want the kernel to be X minus 2. So this X should go to 2. Okay, so the X minus 2 is the polynomial that evaluates to 0. Okay or not? Okay. So this is the surjective map you have. Yeah. Okay. Or this is the isomorphism you have here. Okay. Whenever we talk about isomorphism, right? You really need to know how to write down the map. Okay. What map give you this isomorphism? You need to know. Okay. Whenever you write down isomorphism. Okay. No. Okay. All right. So under this isomorphism here, X is going to 2. So meaning this isomorphism here, we have Z over. We need to understand this x squared plus 1 in the new ring, okay, or the residue of this x squared plus 1 under this isomorphism. So x becomes 2. So 2 squared plus 1 becomes 5. Okay, so it becomes ideal generated by 5. Okay, so in this case here, we get Z mod 5Z. Okay, Z mod 5Z. Since 5 is a prime number, right? Okay, Z mod 5Z is a field. So that's why we call it F5. Okay, so Z mod 5Z is a field. Is a field. Since P is prime. Okay. Okay. Last time we talked about when Z mod NZ has the multiplicative inverses for all the non-zero elements. It is exactly when N is prime. Okay. 5 is prime. You can try and try and find what is the inverse of 1. What is the inverse of 2? What is the inverse of 3? What's the inverse of 4? Okay, what's the multiplicative inverse for this number in this ring? Okay. Okay. But last time I challenged you. Can you write down what's the 5 coset here? What's the 5 representative in the left coset here? On the right hand side here, this is just 0, 1, 2, 3, 4, 5, right? How about the coset here? What's the representative for them? Okay, in the quotient ring. How do you see the 5 elements in the quotient ring? Okay, so I will start by looking at this guy here, Zx over x squared plus 1, comma x minus 2. Okay, let's start by looking at this guy. So let's keep this ring in mind. Okay, so we start by one. We start one by one. So let's look at Zx first. What is Zx? Okay, polynomial ring with one variable. What are these elements? These are what? These are the finite combination of monomials in terms of the power of x. Okay, so we write it in this form here. So it's a finite linear combination of monomials in x. Okay. Should be n here. Okay, right. Get it? Everyone can get this stage or not? Element of a polynomial ring. For example, what? Let me write down some examples here. So for example, 1 plus x squared plus 3x cubed, right? For example. Okay. And then next stage, what can we do? We can quotient by s squared plus 1, the ideal generated by s squared plus 1. Okay. After quotienting, what are these elements here? Quotient by s squared plus 1 means what? All the higher power greater or equal than 2, they are all killed by the ideal. Okay, they are all killed by the ideal. Okay, so what do we left? So we are left with, for example, ax plus b, okay, plus this ideal, because this is a quotient ring. Okay, so this is my coset here. Okay? Because higher degree terms will live inside the ideal. So for example, what? For example, let's give you an example. So let's give an example. So for example, x plus I, x plus 1, and so maybe I should write in this one 1 plus x, and then 1 plus x be 2 plus x squared. And can you see that these two living in the same coset? Can you see that the two live in the same coset? Why? Because I can rewrite 2 plus 1, 2 plus x squared as 1 plus x plus s squared plus 1. Okay, so it is something plus something in the ideal. Okay, so this guy is living in the same coset of 1 plus x. Okay or not? Yeah. So maybe another question. S cube live in which coset? Who has the same coset with S cube? Minus 1? Minus 1. Sorry? S cube live with this live in which coset? In the form of ax plus b. How to work it out? So say again, s cube plus x squared plus 1. Sure, this is the same, but I want the coset in this representative, ax plus b. Okay, I don't want the higher. Of course, I can add multiple of x squared plus 1 here. They all live in the same coset. Right. But can I reduce to this form or not? Okay, lower degree form. Okay, how do I reduce it? So I can rewrite x cubed by x times x squared. Okay, to create something in the ideal, right, I still need a plus 1. So I can, what can I do? I can do a magic. So this is the magic that we always do in mathematics. So I plus minus 1. Then what? Then this is x times x squared plus 1 minus x. So meaning what? S cubed is equals to minus plus x times x squared plus 1. But what is this? What is this? This is something in the ideal generated by s squared minus plus 1. Okay, so this means what? This elements here is living in the coset of minus x plus the ideal generated by x squared plus 1. Okay, so s cubed has the is living in the same coset as minus x. Okay, under this quotient ring, x cubed is the same as minus x. Okay, so this is how we can reduce the degree of the element in my polynomial. Okay, under this quotient. Make sense? Okay. Yeah. Okay, so I reduce to this stage. So we have one more thing to get rid is s minus 2 here. Okay, to reach the goal we want. Okay, we still need to take away x minus 2. So the question is, how does this final ring looks like? Zx over x squared plus 1, and then taking away x minus 2 again. Okay, so we are left with ax plus b now. We want to take away x plus 2, x minus 2, sorry. Yeah. Okay, so how do we do this? Okay, how do we do this? Sorry? Don't understand what you say. Do the same for x minus 2. How to do the same? Do what? Choose the x squared. Oh, you mean, uh, you mean, you mean, introduce x, taking away x minus 2. So, sure. So what do you get? So out of these, so Ziqian suggests that out of these elements, okay, you check, what are in the same coset if you quotient further by x minus 2. Okay, if you allow the multiple of x minus 2, like what we did just now. So how do you do it? Can you reduce to something meaningful or not? Minus 2? I don't get what I said. Yeah.
So for the first example, you reduce. Then there is the step to reduce or not, or is a generalization.
Which one? Which one? You mean this one? This, yeah, below one.
It's just so example how we can write in the form. It's
Yeah.
a way to reduce it to this kind of form. Actually, this is better to reduce.
Oh, okay, yeah, okay, right. So yeah, okay, right, sure, okay. So this is the method that you can generalize to see why we have ax plus b. Yeah. Okay, so you can imagine you have higher power and a more linear combination. Then you can reduce to the multiple of x2 plus 1, like this. Actually, what I'm doing here is using the division with remainder. Division by remainder here. Okay, I'm doing division by remainder because I write s cubed as a quotient times the polynomial that I want to divide with plus some remainder here. Okay, actually what I do is division by remainder. Okay. Yeah, so you could make a remark here. You could use division with remainder to see these are the concept. Okay. Okay. Okay, because when you divide, your degree must be, the remainder must have degree less than x squared plus 1. So which is 1 degree lower than x plus b. Make sense? Okay. Yeah. So how should we do this? X minus 2.
Something ax squared plus 1, a times x squared plus 1 plus a times x squared plus 1.
I don't get what you're saying.
So just divide 2 times.
Divide 2 times. You mean divide
and take the remainder and then use x minus 2.
divide ax plus b by x minus 2.
Yeah.
You can, but I'm not sure you can get to 5 elements or not. Yeah, maybe you can try. Try and divide ax plus b, divide by x minus 2. What do you get? Yes. Which one? No, you should write it out. No, it's not what you think. You should try. You should try. Maybe, should we try? I haven't tried yet. I have another method, but maybe we tried it. So let's take ax plus b. Let's see what happened. Okay, we divide further by x minus 2. I should get what? I should get a x minus 2b 2. Okay, and then I have a minus 2, so I need to add 2a in. Okay, and then I have a plus b here. Correct or not? Okay, so I can reduce a polynomial of ax plus b into a form of 2a plus b. Okay, so this ax plus b here will live in the same coset as 2a plus b plus x minus 2. I think that's all I can do. But just now I tell you there's only 5 things here, right? So how is this a 5 thing? Just now A, B works for any A, any B, right? Yeah, so how is it 5 things here? So that means what? There's one more thing hiding in this relation here. There's one thing you kill it when you kill both of this. Yes. There's something else you kill it. Okay, there's something else you kill it. Let's do one trick. So let's see what's the extra thing that you kill it. So we can do some linear combination between these two. Because these two, in principle, they are 0, right? 0 in the equivalent class. So zeros, if you take 0 square, it's still 0. 0 minus 0 square is still 0. Okay, so let's see this thing will create something interesting or not. Okay, so let's see what's the difference here. X squared plus 1 minus x squared minus 2x plus 4a. Correct or not? Wrong, right? So it's minus 4x. Okay, minus 4x plus 4. This. Okay, correct. Expanding. Okay, and then what else do I get? I get x squared plus 1 minus x squared plus 4x minus 4. Okay, then I reduce it. What do I get? I get 4x plus 1 minus 4, which is minus 3. Okay, not very interesting yet, right? But not that we can divide by x minus 2 again. So let's do the division by remainder. I get 4 times x minus 2. So I need to introduce a further 8, okay, to compensate with the minus 2 times 4. And what do you see? What do you see? You see that 5 is living in the coset of 0. When you actually see that 5, okay, if this is not clear to you, so let me rewrite this. So 5 is equals to x squared plus 1 minus x minus 2 squared minus 4 times x minus 2. So this guy here is always living in the coset generated by x squared plus 1 and x minus 2. Which means what? Which means 5 is living in this ideal. Okay, 5 is living in this ideal. So actually you kill 5. Okay, so you don't just kill, you just reduce to integer, but you also kill the number 5. Okay, so 5 is living in the ideal that you kill. Okay, 5 is the same coset as the 0. Living in the same coset as 0. Okay. Okay. So what's the elements here then? So the elements here is like the ideal x squared plus 1 comma x minus 2, and then 1 plus this ideal, 2 plus this ideal, 2 plus this ideal, 2, 2, 2, 2, 2 plus x squared plus 1 x minus 2, and then 3 plus this ideal, and then 4 plus this ideal. So 5 is killed in this quotient ring. So meaning that this quotient ring is a characteristic of 5. Yeah. Make sense? Okay. Okay. Oh, good. I think this case is easier because the representative is also integer. Maybe in some case, the representatives might not be integer, might be something else, but they are isomorphic to Z mod 5Z. Okay. Sorry. How to get 10? Why do you want to get 10? You mean what is the coset of 10 plus the ideal? Equal to? Yeah, 10 is as a multiple of 5, right? So it should be the same ideal as the 0, the equivalent class over identity. How to find 10? So okay, let me rephrase your question. Is it what I understand? So you want to look at 10 plus this, 10 plus this, is it? Right. Okay. So actually from what we have shown is actually 10 plus this ideal is equal to 10 plus x plus 1, x minus 2, and actually 5. 5 is in there. Correct one. Let me think. I think not quite. Okay, so you mean how to write 10 as 0 plus something in this idea? Okay, good. Okay, good. Very good. Okay. So how to see that this idea is equal to 0 plus x squared plus 1 comma x minus 2? Okay, how to see this? All right, so let's follow what we say. So 10 is equal to what? So we want to prove this. Okay, 10 is equal to plus 5 plus 5. But do we know about 5? Yes, this is the 5. And then this linear combination is living in the ideal. So if you add two things in the ideal, you still stay inside the ideal. So this whole thing is still living in x squared plus 1 comma x minus 2. Okay or not? Okay, actually in other words means what? In other words, the ideal generated by x squared plus 1 comma x minus 2 is the same as the ideal generated by x squared plus 1, x minus 2, and 5. Okay, because I can create 5 using these two. Is it correct or not? I can use 5. Okay, I can create 5 using these two number. Yeah, I think that's right. Okay, they are equal. So you should check the two subset inclusion here. Okay, are all the elements living in here? Okay, this one obvious. Left to right is obvious. Okay, how about right to left? Obvious. Right to left. Yeah, I think it's obvious. Because yeah, obvious. Huh?
Because something inside
Mm.
the idea.
Mm.
Then you add anything inside the idea for this generator, it's also same, right?
It's also the same. Yeah. Let me think.
Also.
Yes. Okay. So I think you are right. So let's formulate again. Okay. So you are in the right track on the in abstract algebra. So we're trying to abstract more again. So what's the statement? So okay. So let's say suppose. Wait. Let me think. Let me think how to rephrase the statement here. So we want to rephrase the proposition. Suppose I is an ideal. Okay. And U is an element of I. Okay. Then I should be equals to the ideal generated by I and U. Okay, so this is the statement. Want to prove this? So how about let's prove this? I think some of you are quite interested in this. So let's prove this. So first of all, I is a subset of I generated by I and U is clear. Right? It's obviously true. Yeah. How about the other direction? Want to show the ideal generated by I and U is an subset of I. Okay. So the ideal generated by I and U is what? Take and X in the ideal generated by I and U. This is what? We can write X equals to what? Equals to a linear combination of things in I and times U. Linear combination of I and U. Okay, so X is equals to A times I plus BU for some AB in the ring. Okay, what ring is this? This is the ring that the ideal live in. Okay, the ideal in a ring R, let's say. Okay, and then for some I as well. Okay, there's some I that realize this item here. Okay. But what? But X is in I also because I and you are in I, and I is closed under multiplication, closed under addition, multiplication by the ring elements. Okay? Yes. Right. Okay, so this is the general statement here. Okay. Okay. No? So just now we create 5 from the 2 generators. So we can add the 5 into my generators. Yeah. Okay. Yeah, so there's an extra thing that we kill, which is 5. So that's why we reduce all the integer to mod 5 inside my code set. Okay. Any question? Hopefully you can use this example to see how to write the code set inside your assignment. Okay, how to see those quotient rings. Okay, what are the elements in there? Okay, and then how to show 2 things is in the same code set. Okay, any question about this? How to see 2 elements is in the same code set, living in the same code set, or how to see the code set inside quotient rings? Any question or not about this? So please don't get pure maths wrong. There's something really concrete you have to do. Yeah, maybe sometimes we just talk about theory or methods, but you really need to sit down and write it out. Okay, it's not something that I tell you, then you can know immediately. If you can do that, then probably you are a genius. Okay. Yeah. So if you are not a genius, then you need to work hard. Okay or not? Yeah. Any question before we proceed? If no question, how about we take a breakfast and then we will go all the way up to 5 o'clock later. We cannot drag for today's because I got FYP presentation to attend. So hopefully we can finish within expected time. So let's return at 3:55.
突然加一个5进去啊，还有一个，本来那两个其实是个 basis，它 spec 完整个 set，我们
不好用 basis，用 generator 比较好啊，因为我们可以互乘。那两个可以互乘，不用，可以互乘哦。generator，所以这个是 generator 跟 basis 的差别。
对，我本来那两个已经 generate 完整个 set 了，对，我现在只是加一个东西进去，然后它是 dependent on 前面两个的。它跟前面两个其实没有对，
因为如果你把前面两个丢掉，然后把5丢进去啊，其实你
就set 完整个
做不出另外一个东西。哎，也没有什么，不确定哦，不确定，我只找一个5出来，不知道还不会找出其他东西，我不懂啦，可能应该不会这个 case，但是 in general 来说，你要讲 check 完全部我是不知道。对，因为这一个情况是我是从另外一个方向知道我只有5个东西啊，所以应该只有这个东西你要 Q，other than 那两个。
等一下，这样我这样做应该错完了啊。
哪一个？
因为我这边全部题目就跟你一样的想法，就是我把这两个东西，
看下哦，哎呀 ，OK， 等一下我要讲，这题有代波，这有代波，这个是1来的，哦，不然你不会切这个东西。
切到3个，
切不到哎，你想切到啥？
切啊？
那你切，你能切到什么？
那你切，我现在看你啊。哦，我就这样做，
这样做。
我就拿6
嗯
乘 x，然后点这个乘3。我不可以乘 x 哦。
可以，因为它是那个 ring 里面的 element，所以是可以。6x 减那个你拿到
我6x 减3乘
6x 减啊，给我想一下。
你这应该是6乘以。
哦，哎，给我想一下啊。
诶，这好像他自己的，他自己的，
看一下，给我
好像是他自己的。
6x
点6x 减6x 加6，他自己的，对哦，他是这个6了。
对，哦，他自己哈，哦，OK 咯，这样
他就跑回去。
这样你没有变新的东西出来，我以为你有变新的东西，
我这错，
因为不然的话这个东西做不出来。
他不是切好让他回去 Z6。
对，Z6，但是你2x 减2，我没有教过你讲切东西。
等一下，所以你是我们切这东西，还是 check 它是什么吧？
一样哦，你要 check 的话，你就要切了，不然的话你 start 在这一个 step，你 start 在一个 quotient 里。
哦，如果我
或者
你再帮他做，就不是你了。
哪一个？
因为我现在每一题都是用你这个方法做过来。
对啊，就是这样做啊，就是这样做啊，就是这样做啊。但是我是说这个有带波，这个有带波，但是你不能用这种方式切出来。如果你要做这题的话，它不能够用这种方式切出来，因为它这个东西是如果用还没有 introduce 啊，就是 irreduce，这个是 reducible 的东西。你看我给你的东西都是 irreducible，就是你一定要 attach root 上去。如果要 root，yeah，
什么意思叫 attach root？
就是比如说 x square 加1啊，我要 attach 那个 root 上去。
哦，就是 x square 加1，
因为它是 irreducible，但是这个不是 irreducible。But anyway，反正就是切不了这个东西就对了。呀，这个有带波，等一下讲一下，忘记讲。
然后这一题去到
为什么这样做？
一样，我就直接拿这个乘2，这个乘，
哦
然后这样相减一下。
哦。如果你达到1的话，不是意思说你要把1送去0了，像这个整个东西不是你把全部东西都送去0，
负一。
负1送去0的话，不是代表1也送去0吗？
啊，对啊。
所以你就 Q 完全部东西哦。
哇，
这题东西是0，这题是0吗？
我把你那个世界杀掉了。
对啊，
对啊，
答案对嘛？是吗？是0啊？你这个是0啊？你说他
对，我懂，没，
你还没有做。
我做什么？
你做什么？
做什么
428哦，所以是3。
呀！这个是还好 OK，然后这是15啊。我直接拿这个乘 x square，然后想减。
为什么你不要直接杀5先呢？像刚才我那样吗？杀2先，还是杀1？杀了5过后，然这个就是变成 residue 哦。我想想，对，525不是，哎，对，525。OK，你算出来是多少？我算我的，你算你的。
是直接拿乘5减3。
你是15啊？你算到15啊？我想一下啊，525，我算到这陌生这，给我想一下。
对啊。
不对，我不对。OK，你算这个，你讲错啊，你讲错。
因为这个是 x square 加3嘛，在这边我要把 x square 删掉，所以我直接拿这个乘0，然后这个减 x square，然后我就把 x square 删掉了，剩15啊。
这样你还没有把 x 杀掉啊？你只是说我把 z 变成 z mod 15还有 x 躲在里面，你只是加多一个15进去嘛，对不对？但是你加多一个15进去，你还里面已经有5了，其实哦。
哦，
所以你其实已经可以把这个 coefficient ring 切成 z mod 5z。所以你剩的是你要问，在 z mod 5zx 里面有没有一个东西是可以让你 square 成 x。
OK，
为什么 square 成 sorry square 了过后加 x 等于0。 有没有这样的东西？如果没有这样的东西的话，就 join 那个 ring。
我明白，我明白，我在做什么鬼啊？因为我不懂我在做什么，我只知道我三个东西。
耶，OK，
为什么要对了？
因为我跟这边，我以为这边做东西就可以删。
还是说讲2要加3个？
没有剩下的 element 有没有东西 square 了加上等于？
就在切5了过后，还有
就0、1、2、3、4啊，这4个东西 square 了过后加上有没有等于？在 mod 3。那如果不能的话，你就像那个 Rx 切 S square 加 I 这样 adjoin 一个 adjoin 一个 adjoin 那个 I。
要这就要切。然后这个没有10，我们
没有。
OK 啊。
我这样说啊，suppose 它有了 and then yeah，suppose and then contradiction。
做这种，
我忘记 contradiction 长怎样了，
这应该不对啊，不可能这样简单。
忘记 contradiction 长怎样，但是是 contradiction。suppose 还是
没有啊，为什么这个会很我们想要切的话是让它变0。
啊00，那个是 identity，
哦，
不是
然
multiplication。
后这里的 F 跟这里不一定要不一样，你要先取一个全。对对，然后
对，我应该要先找，假设有 X，我假设 X 其中啊，然后我就讲 X 会 send 去一个地方，然后这样子做下去应该会遇到一个 connection。
不可以乱 send，应该不可以乱 send。你要 define 一个 well defined map 先吗？
应该是就是这两个可能之间的，
就是说你要
这两个 question idea 之间的一个 map。
之间的一个 map。什么意思？但是我的意思是说，因为它是个 homomorphism 嘛，它0一定要送去0，所以这边被 kill 的东西一定要被送去过后也被 kill， 你就要 make sure 这些哦。这有点像上次我们说两个两个一样的 pattern， time for group 跟那个 z for 嘛，suppose 有个 isomorphism，然后什么会发生
所以你可能做第一次没有人做多了，这就不见了，就没有。
something like that， 就是I mean 你呀，你可能要 contradict 它的 ring 很像。来看，
那你这一题是要我说的，
找可能
这个 map 的可能。
，yeah， 找那个。Okay, there's a typo in your assignment 2. I already fixed it on the Moodle. It is question 5, 5B, 5B. Yeah, so please check it out. So there's a typo here. Number 5, question 2B. Most of these questions are from textbook. So if you want to check, right, you can check the textbook version. Here. What did I wrote? 2B, right? Is it 2B? Yeah, 2B. So it's this 2x plus minus 1, not 2x minus 2. You haven't learned how to do that yet. If I gonna put 2x minus 2, maybe we need something called the Chinese remainder theorem for ideal. You can make this if you go further in algebra. Okay. So for now, we only have so I want to say, okay. So this is a typo. So please download the new the latest version. If you met any question about this tutorial, right? Not tutorial, assignment, right? Maybe you can ask next week. Okay, next week is the last week to do this, so you can ask us next week, and then we can try and address it in the class. Okay, so let's continue. We have to be quick. Okay, so last time where we stopped, we stopped at the one theorem or proposition. Okay, so this is the proposition where we stop. So we have a ring. Okay, we have a monic polynomial. And then we create this new ring called the R adjoint alpha. And then what is this alpha? Alpha is the root of my monic polynomial. Okay, and then there's a claim here. Okay, there is some claim here. So we let R alpha denote the ring Rx quotient F. Okay. And then actually we write some isomorphism between these two things, right? So let's write down here. So let's write down the construction. Okay, we have this where R is a ring, F is monic. Okay, so monic F in Rx in the polynomial ring, and then alpha is the thing that evaluated to 0 by this. Okay, so can understand this? All this notation. So you should ask. I write isomorphism, right? What's the isomorphism that give me this? Okay, what's the isomorphism that give this? What's the isomorphism that give this? Yeah. Okay. Yes. Good. So you just simply send x or alpha to x because this is the isomorphism. You can do either way, and then they are inverse of each other. Okay. So this is the isomorphism we refer to. Of course, when I say isomorphism, right, this word contains a lot of things. Homomorphism, isomorphic, injective, bijective, surjective. Check it. Okay, you can check it. Okay, you can check it. Or you just use first isomorphism theorem, because this map is actually a surjective map. Okay, and then the kernel of this map is the polynomial that sends the alpha to 0. Okay, what's the kernel of this map? Okay, it's the polynomial that evaluated to 0. This is given by your f. Okay, because this is exactly the setting of my alpha. So let's call this map phi. Okay, then I'll say that kernel of phi is generated by the polynomial f. Okay. Then by first isomorphism theorem, you will get the isomorphism. You know. Yeah. And then if you like, phi is also surjective. Okay. Because I already decide where x should go. It goes to alpha. And then everything on the left-hand side is decided by the coefficient of alpha. So alpha has a pre-image. What's the pre-image of the coefficient? We just fix the coefficient. Okay. R goes to R. Okay. There's a lot of things you should check. One thing that I'm very scared to teach this class, your class, is because you don't know what you want to check. You want people to tell you what you need to check. People cannot tell you everything, you know. I can only tell you some principle, and then you should go and check put your effort, go and find how to check it. I cannot tell you everything, every line, every method, how to check things, you know. You get me or not? There are too much things to say. Okay. So you need to put effort, go and find how to check. Otherwise, your learning speed is very, very slow. And you cannot learn much. Maybe you hear like I'm scoring you, but it's really my sincere advice to you. If you're going to learn with the old way, you cannot learn much. And you have only 1 year to go, I believe. And after that, if you're not going to study, you're going to work. I'm not sure you are still learning or not after that stage. But once you go into working life, there's more restriction on you. It's even harder for you to learn or study. Okay, I hope you can change your style if you wish to study more. Learn more new stuff. Okay? Okay. Yeah. So meaning, if I tell you the kernel is this generated by this f, then you should check why is it true. Okay. If I tell you why phi is surjective, why? Check, prove it. Okay. You have to prove it. Okay. So this is the isomorphism. So, and then there are 3 things here, A, B, C. So A, you can see that actually 1 up to alpha n minus 1. So what's this n here? So this n here refer to the degree of your polynomial. Okay. You should imagine this n as the degree of your monic polynomial. Like just now, right? What we have done just now. So what's the example we have just now? Okay. The example I have just now is this x squared plus 1. See? So this is a monic polynomial with degree 2. So what is left over is just degree less than 2. Okay? N minus 1. Or 2 minus 1 here. Okay? X to the 2 minus 1. So we have x1 and then up to 1. So s1 and s0, which is 1. Okay? And then we stop there. Okay? And how to add two elements in this quotient ring here. Okay, we just add it by coefficient with the same monomial. Okay, how to multiply them together? Okay, so we just multiply the 2 polynomials that realize the item in R alpha. Okay, after substituting by alpha, and then we can do the division by remainder. Okay. And then you can see that FQ is the thing that lives in the ideal killed by the quotient ring. Then you are left with the remainder. So I use an example here. So I use the example of the complex number. Okay, how we build complex number. So recall that the complex number C is equals to what? R adjoint X quotient by S squared plus 1. This polynomial here. Okay, because we cannot find the root of S squared plus 1 in real, because the root of this polynomial is square root minus 1. It's not real number. Okay, so we call this number a new number, which is I. Okay, we call it a new number I. R adjoint I. Okay, so whenever we write this, right, this adjoint I, you cannot think of it as just an intermediate or variable anymore. You need to remember this I is a special I that satisfies I squared plus 1 equals to 0, or I squared equals to minus 1. Okay. So in this case here, do you have I squared inside this complex number or not? Don't have, right? Because I square will immediately convert to -1. Okay, so that's why I1 and I form the basis in the ring of R adjoint I. Okay, and then you can relate this to the monic polynomial that have I as the root. Okay, because the monic polynomial that have I as a root has degree 2. Okay. Yeah. Should we prove this? I think. Okay, first of all, any question about this statement first? Probably we won't prove it because I think it's not very enlightening for you. But I want you to use this proposition here. Any question about this proposition or not? Any statement that you Malay, we say ragu ragu. You have doubt. Do you have any doubt on this statement? Are you clear what this statement tells you? Please learn to speak up your Chinese. We say 诉求. What's English? 明修. 诉求. Your needs. Okay, please speak out your need. People cannot guess your need. Okay, please learn to speak out your need. Okay, 提出你的诉求. Maybe people won't satisfy your needs, but at least you need let people know. Okay, what's your need? 不一定你所有的诉求会被满足，但是至少你要提出。Okay, does everyone has any question about this statement here? If not, maybe we do one more example. Let's see one more example than the complex. I will attach the proof later in the lecture notes, but I think it's more important to see how it works. So let's look at one map from Zx to C. Okay, let's look at this map here. So sending x to the root of cube root 2. So what's the kernel of this map? What's the kernel of this map? You know what's the kernel of this map? What's the polynomial that gets sent to 0 under this map here? S cubed minus 2. And then you should check that this is actually the lowest degree polynomial that does this, that gets sent to 0. Okay. And then you can use division with algorithm, division with remainder to show that the kernel is indeed generated by s cubed minus 2. Because if you consider lower polynomial, ax squared plus bx plus c, if you sub the root in, can you get 0 or not? Can you? No. Okay. This is similar to what we have discussed last time. Okay. So by first isomorphism, what can we do? This map, wow, let me see. I think I put something wrong here. Let me see. Okay, never mind. So it's okay. So let's continue. So by first isomorphism theorem, what do we have? Okay, similar to what we have done just now, this quotient ring here is isomorphic to Z adjoint alpha. Okay, so not alpha, we call it gamma. So gamma. Okay, what's this map? Just now Mingxiu told us this map, right? You just send x to the gamma. Okay. So by the proposition before, by proposition before, 1 comma gamma square is a Z basis for my new ring Z adjoint alpha. Okay, so what do we mean by this? So let's do some concrete example here. Okay, let's do some concrete example. And then proof will look similar to this calculation. So let's say, what are the elements in Z alpha? Okay, what are the elements in Z alpha? For example, we can take gamma square minus gamma and beta square, gamma square plus 1. Okay, and then let's consider what is beta 1, beta 2. Okay, what's beta 1, beta 2? Right. Okay, so beta 1, beta 2 is what? Anyone quickly compute this? Anyone quickly compute this? Sorry? R4 minus gamma cube plus gamma square minus gamma. Okay, but just now I say that 1 gamma and gamma square is the basis, right? But how about this gamma 4, and gamma 3? What happened to them? Can I reduce to 1 gamma and gamma square or not? How? Huh? I don't say I can. How? How? Yeah? What do you mean by linear combination? Yeah, how to reduce this higher degree term? Divide by what? Divide by what? Divide by the F alpha, right? Because F alpha is the thing gets sent to 0. Okay or not? Okay. So we can reduce this. Okay, I can reduce this. Or how should we reduce this? Let me see here. So what is F alpha? Let's keep F alpha here. So F alpha, F gamma is equals to gamma Q minus 2. Okay. So we can reduce polynomial with a higher degree than 3. Okay. How should we do this? What's the easiest convenient way? Okay, so let's do this. So we have y times y cube minus y cube plus y squared minus y minus gamma. Okay, and then we can try and pull this gamma 3 out first. So we can only kill gamma 3 minus 2. Okay, this is the thing living in my ideal. But I have gamma 3 here. So I need to add 2. Okay, I need to add 2. Minus 2 or add 2 to it. So I get gamma minus 1 times gamma cube minus 2. And then I need to add it back. So 2 times gamma minus 1. That's gamma squared. Okay. Okay. So what do we get? We get plus gamma squared, 2 gamma minus gamma is plus gamma, and then minus 1. Is it minus 1? Or minus 2? Okay, so this means what? So this means beta 1 and beta 2 is equivalent to gamma 2 plus gamma minus 2 modulo, or if we kill the ideal of gamma cube minus 2. Because why? Because we remember, what does this alpha satisfy? This alpha satisfy gamma cube minus 2 equals to 0. Okay, so this terms here becomes 0. Okay, or in other words, what we are doing modulo gamma 3 minus 2. Okay. Yeah. Okay. Any question? Any question? Yeah. So you see, if I write in this form, isn't it a bit like the integer modulo arithmetic? Yeah, so that's why just now I comment about the Chinese remainder theorem for ideals, because what we're really doing is just modulo the multiples, okay, that generated by the elements in the ideal. Okay. The difference between modulo arithmetic and now is we allow more things inside the ideal. Because in arithmetic, if you say modulo 2, you just modulo the multiple of 2. But now, inside my ideal, I can put multiple generator. Okay, A1, A2, A3. And then all these things, I kill it. But in integer modulo, you just kill, let's say, modulo 6, you just kill multiple of 6. Modulo 5, you just kill multiple of 5. Okay, no? Okay, so we are generalizing the integer modulo arithmetic. Okay, when we kill this ideal. Does it make sense? Can you see why we can reduce the elements in Z alpha to the basis that contains powers of alpha up to n minus 1, where n is the degree of the polynomial that alpha, that this root evaluated to 0. Okay. A bit long, but any question? Any question? Any part you don't understand about, you can ask, and I'll try and answer. Yes. Second, which line? From top, from bottom. Yeah. Oh, you mean, oh, you can, I mean, wait, let me think how to say this. Yeah, okay, again, okay. So you are saying that, can we just do like a substitution? Okay, whenever we see, because we know that, okay, so, okay, like this. So since we know that y cubed minus 2 equals to 0, so can we do substitution like gamma 3 equals to 2? Is that what you're saying? Yeah. So let's try it. So let's try it first. So this is equal to what? 2 times gamma minus 2 plus gamma square minus gamma. This is what? This is also equal to gamma square plus gamma minus 2. You can do this substitution. Okay, but why I do the division with remainder method is because this is the general method they use to prove the statement. Okay, yeah, but the result is just substitution, correct? Yes, you can use it. You can use it. So because it is because of this equation that the root satisfies, so that you can use it. Okay, you can use it not because I say can use, you use it's because it can be used. only it can be used. You know or not? So there's subtlety difference here. It's not because I say you can use, then you use. You must know why I say you can use. It's different, no? Okay. Okay. So if I say can use, there must be a reason. If I don't know the reason, then you need to find out the reason. Okay. It's not because people ask you to do, then you do. You must know why you are doing it. Okay. Yeah. So you can see that Wenzhou way maybe much shorter, right? Much shorter to get the result. But what I present here is the general method to see. Okay, general way, which is the division with remainder. And then this way will help you to read the proof inside the book, or later I will write it to my lecture notes. Okay. Yeah. Any other question before we proceed? This is very helpful in your assignment. You need this adjoining root of your polynomial. Otherwise, you will build some funny rings out if you simply quotient. Okay. Any other question before we proceed? Okay. So let's continue. So we will go to a product ring. So let's go to product ring. So last time we talked about product groups, right? So rings is similar. Again, rings is similar. So if you want to define product rings, you need to tell me what's the LLC. Okay, what are the two LLC you want to define? How to add two elements in the product rings? How to multiply two elements in the product rings? And then check that they are indeed the LLC. And then what are the identity maps? Okay. So let's take two first. Okay. Two rings. Okay. And what is the product ring? On the set level, we just take the product set or the Cartesian product. Okay, XY product. It's like you can imagine R, real number is a ring. Okay, R squared is another ring, Cartesian product. Okay, R squared. So one prototype you can think of it is R squared, calculus R squared. Okay, how you add the two elements there, how to multiply. Okay, we haven't learned multiply there, right? So let's do it here. So the product set is a ring, which is called the product ring. With component wise, okay, we call it a component wise addition and multiplication. Okay, so what do you mean by components wise? If I have x prime plus y prime, where all the x prime, y and y prime are from the ring of r and r prime respectively, we will just add the first coordinate up and then add up the second coordinate up. Okay, and then how to multiply? I just multiply the first component together and then multiply the second component together. So this is called a components wise. Okay. So can you guess what's the additive and multiplicative identity here? Can you guess what's the additive identities and the multiplicative identity here? Additive identity is 0, 0, and the multiplicative identity is 1, 1. Okay, 1, 1. Okay, respective. Okay. Okay. So there are some other properties you can see. So we can look at projections. Okay. We can just look at one component, for example. We can project to R, or we can project to R prime. Okay or not? What does this projection do? I can take x prime sends to x, or we can take x prime sends to x prime. Okay, I just read the first component, or I just read the second component. And you can show that these are trivially a ring homomorphism. Okay, it should be easy to check. This is a ring homomorphism. And then, what's the kernel of these two maps? Can you see what's the kernel of the two maps? First of all, they have to be ideals. So what's the kernel of the two maps? For example, what's the thing that gets sent to 0 in pi? By pi. Sorry? X and 0. 0 and x. So meaning 0 cross the whole ring. Okay, R prime. And similarly, the other one you have, okay, this one should call R prime, pi prime. So the other one we should have R cross with 0. Okay. Okay. Let me see. So there's one very interesting thing here. There's one very interesting thing here. So this kernel, right? So for example, the kernel of R cross 0 of pi prime is actually what? Is actually a ring. Okay, last time we say that ideals is almost rings, but what? But ideal usually don't contain the multiplicative identity. If it contains the multiplicative identity, then it is the whole ring. Okay, but in this case here, pi R cross 0 is a ring. Can you see why is it a ring? First of all, R is a ring. But in the other component, what do you have? You always have 0 ring. It's a 0 ring. So what's the multiplicative identity here? 0, 1. You sure? There's only 0 on the second component. Where's the 1? Right. Okay. So the multiplicative identity is actually what? 1, 0. Correct. Okay. So it is actually 1, 0. Okay. But this is not a subring. Okay, but this is not a subring. So let me add. This is not a subring of R cross R prime. Okay, unless R prime is the 0 ring. Okay, it's not a subring, but itself is a ring. Okay, it is itself a ring. Okay, so I would say similarly for 0 cross R prime. Okay. 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 This E is a very important, a very interesting thing. This E has a property, which we will introduce now. It will satisfy some relation called the idempotent. What is an idempotent here? So idempotent of a rings is something, okay? It's something when you square, you go back to your self. E squared equals to E. So you can see that if you compose 1, 0 with 1, 0, you should get 0. Okay, so this idempotent is very important in mathematics, even in the frontier research. We will typically use the idempotent to split out the space. For example, what kind of map you have seen actually is an idempotent? For example, projection. Okay, you have a map project to the other space, and then you project again. You should get the same space. Okay, correct or not? For example, you have orthogonal projection. You have a vector. You orthogonal project it to a plane. From the plane, project to the plane again. Do you get the same line, same vector? Okay, so this is something that is an idempotent, but that one is the operator. Okay, is an operator or a function. Okay, function, simply a function. Okay, so function also behave like a idempotent. This function behave like idempotent. So idempotent here very important. Okay, let's see how important is it. It is. So this proposition is very important, in particularly important for your exam. So we have this proposition here. Let E be an idempotent element of a ring S. Okay. So meaning E square equals to E. Okay. We can create another idempotent. Okay, we can create another idempotent. So the element E prime equals to 1 minus E is also idempotent. Is also an idempotent. Okay. Then we will have E plus E prime equals to the identity, multiplicative identity, and E times E prime, you get 0. Okay. Okay. Should we prove this first, or should we go on? Let's prove this first. Okay, and then we go to different statement. So let's prove this. So is it easy to see why E minus E squared to 1 minus E? Can you compute it? What do you get? 10. What do you get? 1 minus 2E plus E squared. Okay, but E is an idempotent, so you should get 1 minus 2E plus E. And then you will get back your 1 minus E. So it is an idempotent. So how to check the other property? So E plus E prime equals to 1. E plus 1 minus E, which is 1. Because why 1? We need to commute here. But our ring is always commutative. So we can commute. Okay, so this is the place we use commutative here. Okay. How about E times E prime? E times E 1 minus E. You get E minus E squared. But E is an idempotent. E minus E, you get 0. Okay, so it's just simple computation. Okay. Okay, next. Second statement, what can we do? So with the given LOC, okay, from X, the principal ideal, okay, the principal ideal, E times X, okay, is a ring. Okay, it's a ring with identity element E. Okay. And then, we can define a ring homomorphism from X to EX by just multiplication by E. So we can define a multiplication by E to be a ring homomorphism from X to EX. So meaning I take all the element in my ring, I just multiply by E on the right-hand side. Right, this is a ring homomorphism. Okay. Can you quickly see why is this a ring homomorphism? If I take x plus y here, is it sending to ex plus ey? Okay. If I take, okay, let's call this phi. So let's prove this. So let's prove first E is the ring homomorphism. Okay, so one, can you check that? Do I send phi p1 in x to phi1 to 1 in ex? Okay. So what is 1 in ex here? Just now we say that the principal ideal ex is a ring with identity E. Okay, is it true? In ex, there's all the element is E times x. Okay, every element is E times x. So what's the thing that multiply to ex, get back ex? Oh, x in ex, okay. Let's ex multiplicative. So let me put more spaces. Multiplicative, multiplicative, multiplicative identity y will satisfy yx equals to y ex. So ex equals to identity. So no, not identity, equals to x. Okay, so what is the y that does this? I want to see what's the y that does this. Okay. Not that I don't write down x, y. Why? Because my ring is commutative. I just need to check one. Okay, my ring is commutative. So, what is x? Since x is in ex, there exists xi in x such that x equals to e times x1. Okay. So you want to find something that y times ex1 equals to ex. Okay. What is the y that does this? E is a idempotent. Okay, I can regenerate E become E squared. And then E will do the job. Okay, then you can use the same method of showing the identity is unique to see that by cancellation law. Right. By cancellation law, y equals to E. Okay, so actually you need to send the identity in x to E. Okay, 2. Is this true or not? My map. Okay, so let's remind our map here. So phi is a map. Go from x to ex, sending little s to e times x. Okay. Sending identity to e times identity, you should get identity. How about phi x plus y? Phi x plus y, you should check that it is equal to phi x plus phi y. Okay, which is equivalent to checking e to the x plus y equals to ex plus ey. Okay, how about third one? Phi xy equals to Vx times Vy. Okay. So this is equivalent to checking what? E times xy equals to Ex times Ey. But there's 2E on the right hand side, right? Can you create 1E, extra E for E or not? There are 2E on the right hand side, but there's only 1E on the left hand side. Can you create extra E? How? Depend on how you think about it. Usually we will go from left to right, right? So how to create 2E out of 1E? Huh? Distribution? No. How to distribute? Yeah, because E is an idempotent, right? E is an idempotent. So E xy equals to E squared times xy. Okay, and then you can use commutativity, associativity to rearrange to Ex times y. Okay, no? Okay, so since E is an idempotent, so you can see that the importance of E to be an idempotent here. Okay, so that this ring homomorphism is satisfied. Okay, let's see. There's one statement here. So C. So yeah, let me think. Yeah. Okay. So I'll continue. The ideal Ex is not a subring, okay, of X. Okay, it is not a subring of X, although it's a subset, unless E is the unique element. Okay, is only if E is the identity of X. Okay, and also E prime is just 0. Okay, we can try and show this. Maybe you try and show this. And so the most important result is this one. And this one is very useful in the in future, in your future career, only for maths, pure maths. Okay, so this ring X, actually I can split out the ring using the idempotent, okay, using Ex and E prime X, okay, which is Ex times 1 minus E. Did I define 1 minus E? Yeah, 1 minus E. Okay, so that means if you have a ring X, you have a space X, you got your idempotent, okay, go take your idempotent, multiply with your ring. And then it will split your rings into Ex cross 1 minus E times X. Okay, split into these two product of the two rings. Okay. So I say isomorphism here, right? So that means I need to create the isomorphism for you. So can you think about what's the isomorphism I can take here? Where should I send the element X to? Any guess? What kind of map I should take? Send X to where? Okay, I can just send it to Ex and E prime X. Just like that. Okay, just like that. Okay. Yeah. So what do you need to do? You need to check what? Ring homomorphism. Okay, you need to check ring homomorphism. But ring homomorphism I already checked for you already. Right. Just now I said multiplication by E is a ring homomorphism. Okay, multiplication by idempotent is a ring homomorphism. Okay, so I already checked for you. This define a ring homomorphism. So what else you need to check? Injectivity and surjectivity. Okay, injectivity and surjectivity. So given UV in EX cross E prime X, what's the pre-image? Can you think of what's the pre-image? What's the thing get sent to UV? Okay. What's the thing that gets sent to UV? Hmm? Sorry? E inverse. We can try. So you say E inverse, inverse, E inverse U. Is it? How do you know that E is invertible? Hmm. How do you know if E is invertible or not? Huh? You mean U times V. U times V? Then you should check. So what is UV? E times UV and 1 minus E times UV. Hmm. But what is U and V? U and V are elements in EX and E prime X respectively. So I can write U and V in a more specific form involving E. Okay, then UV actually equals to what? E times x1 comma 1 minus E x2 for some x1 x2 in x. Okay, so maybe we can replace this E times EX1 times comma 1 minus E times EX1 times 1 minus E x2. Does this compute to U and V or not? So here is 1. So what's this? So maybe finish computing this and maybe we will break for next time. Continue next time. So what is this? A E times 1 minus E is what? Is 0. Okay, just now we computed E times E prime is 0. So this part is 0. The other part you also get 0. So you get 0, 0 for this. So it's not that. The claim is should be U plus V. Okay, you can go and try and compute it. U plus V should give you U and V. Okay, so this is the surjectivity part. How about injectivity part? Okay, you need to show for the injectivity part. Okay. Show that the kernel of the map have to be 0. Or show that if Px equal to Py, then x have to be equal to y. Okay, try it. We will do it again. Okay, next week. And then next, for the plan for next week is we will do some fraction 11.6, I believe, 6 or 7. And then maximum ideal. If can, we do some prime ideals. And then before finish, maybe we introduce what is module, just definition of modules. And the exam will be up to this product ring. Okay. No, we still have more, but not examinable. Or maybe let me check first. I scared I forget.
Content also until here.
Content only up to before product ring. Quotient ring, right? Adjoining elements, the product, the assignment. Yeah.
The thing to this,
Yeah, the assignment, I think just up to this adjoining elements part. There's no product ring involved there. But exam will involve at least up to product ring. And then exams start from correspondence theorem of groups. You can take a open neighborhood there and then keep forward until the open neighborhood. So meaning you cannot just learn from there, right? Because if you don't know group, then how you gonna learn correspondence theorem? So open neighborhood are open until wherever you know, right? Clear or not? Yeah. Okay. If you need to learn from start, please do it. Because if you don't know group, how you gonna use correspondence theorem? Clear or not? Yeah. Okay. Any question about the final content or not? Final content score. Next week, yeah, next week ask again. Maybe I go and revise again because few weeks ago we decided. Okay, so see you on the next Tuesday or Wednesday again. Merry Christmas. Yeah, Merry Christmas. Merry Christmas to everyone. Okay. Yeah, enjoy your holiday before your final time. Enjoy your Christmas first.
I did my day class.